All right, so the plan for today is to finish talking about PFK, as well as several other enzymes in glycolysis. So we may finish glycolysis today. If not, we'll finish it Monday and start the citric acid cycle. So when we left off talking about PFK, you're at previous slide one. No idea. There is a slide before this. I don't know what it looks like. Has something to do with PFK. Oh, there it is. All right, so phosphofructokinase phosphorylates F6P to FBP, phosphobis, fructose 1,6-bis phosphate. We're going to use an ATP and the magnesium. It's not a reversible step. And some other things that make PFK an interesting enzyme is that it has this allosteric feedback mechanism. So the T and R states are in equilibrium. And so, much like how we imagine hemoglobin to work, it has a T state and an R state. The inhibitor site binds ATP only in the T state. So as we see here on this figure, glucose in the presence of fructose 6-phosphate, ADP can turn on the mechanism, but phosphoenolpyruvate can turn off the mechanism. And then ATP is both a substrate and an inhibitor. So you need ATP to complete the reaction, but if there's so much ATP in there, it can actually act as an inhibitor. Let's see. Oh, so here, we'll go through this first. So at low ATP concentrations, it's as though there's no inhibitor. And so we reach Vmax, and we see a lot of activity. As we add a little bit of ATP and a little bit of AMP, the activity of the enzyme decreases. And when we add a lot of ATP, the activity of the enzyme actually almost turns off for the same substrate concentration. So that's graphically how you can see that ATP turns it off. Question?
Like how does this change if there's just one ATP versus a lot of ATP? It's just
because it takes up the binding site of the substrate.
But if just one is present, it doesn't take up the
You need one ATP plus one substrate to make the product. If there's a lot of ATP, much more than the substrate concentration. So in this case, ATP concentration is 1 millimolar, but at this point, it's only 0.5 millimolar substrate. There's much more inhibitor than there is activator. Oh, there we go. So the other mechanism that's used to regulate glycolysis, besides the concentration of ATP being too high, which will turn off PFK, is this right down here, phosphofructokinase 2, which, regular Phosphofructokinase goes from fructose 6-phosphate to fructose 1,6-bisphosphate. Phosphofructokinase 2 goes from fructose 6-phosphate to fructose 2,6. So rather than 1,6, it goes to 2,6. So PFK2 is the other enzyme that can regulate glycolysis. So when glucose concentrations are very high, bless you. There's not a cool name for fructose 2,6. So when glucose concentration is very high, PFK2 activates and starts converting some of that fructose 6-phosphate into fructose 2,6-bisphosphate, which, going back to the figure on the previous page, is an activator for this mechanism. So fructose 6-phosphate can either be converted to fructose 1,6-bisphosphate or go through this mechanism and then enter glycolysis again. So it's a way of, it's like a holding pattern, right? You have so much glucose entering that not all of it is able to go straight down through the mechanism. So some of it takes a little detour, hangs out here in the parking lot until it's able to enter traffic again. Right? It's kind of like where you have to take turns merging. This is what it is. Half the traffic can go straight through and half of it has to wait at the stoplight before it's allowed to merge into the glycolysis pathway. Yeah. That's probably been my best analogy this week. Good. Everyone agreed with it right away. That's rare. Most people are like, I don't know what she's talking about. But there's always that one person who nods out of pity, like, sure. I can see that, Paul. Oh, okay. Because I was using in Gen Chem, I was talking about Voltron, which I know is a cartoon that I watched when I was younger. Apparently no one watches it anymore. It's on Netflix. Voltron. It's a Japanese anime cartoon. It was on Saturday mornings, where individual people had robotic cats that they could save the world with, but then the robotic cats could combine to make the big cat, which was Voltron. And so we were talking about the ideal gas law. That individually, the gas laws are good and can save the world, but they can combine to make the super ideal gas law, which is actually even better. So individually, good. Together, even, and then nothing. So I had to go with Power Rangers. Most people have seen Power Rangers, and they, individually can do things, but together they're, yeah. I'll have to go up with something even better soon here, because soon everybody like, I don't know what Power Rangers are. Bless you. So, PFK is the slowest reaction of the 10 in glycolysis. And as such, this reaction determines the flux of glucose through the pathway. So it's kind of the gatekeeper that determines that. Yes, ma'am?
How would you, if you wanted to speed the step up, because it has roadblocks to slow it down?
You could artificially lower the ATP concentration, like suck off the ATP to do other things. That would speed it up. You could increase the concentration of enzyme so that it's just able to do more reactions. Or you could add more of this phosphofructokinase 2, which would pull more of the glucose off, so you could, in theory, push more through the reaction. So. But yeah, this one has the most feedback loops to it, which makes it the RDS for this.
Kind of like the airport.
Kind of like the airport. So there's the runway. You got to take turns taking off. So you can load up all the passengers, but then they still have to wait. Questions about PFK? Good. All right, in that case, let's talk about aldolase. So the enzyme aldolase catalyzes the cleavage of fructose bisphosphate to GAP and DHAP. So this is our cleavage step where we had our 6-membered, 6-carbon molecule, and then we're going to cleave it into 2 3-carbon molecules. So, for those thinking back to organic, when we talked about aldol condensations, this is the reverse. So if I take these two together and imagine going this way with it, that's an aldol condensation. Where you had an aldehyde combining with the alcohol, and it would release a water and form a bond. Yeah. Thank you for nodding out, Pity. I appreciate that. Yes. Reverse aldol condensation. So as you can imagine, a cleavage reaction usually requires energy to force the bonds to break. And as such, the delta G of this reaction is around 20 kilojoules per mole. So what does that say about the likelihood of this reaction occurring on its own without some input? Very unlikely. So this is unfavorable reaction. But luckily, we're going to couple it with some other reactions to make it more favorable. I guess any questions about this one? This one's pretty straightforward. Clips it in half. So now we have 2 molecules ready to enter the next step. So DHAP and GAP are now being made. GAP can continue down the glycolytic pathway. DHAP, however, has to be converted into GAP to continue down the pathway. So we have 2 phosphorylated molecules, right? Glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, both of which have a phosphate group on carbon number 3, which is good, but for the next enzyme to be able to use it, it has to have an aldehyde at carbon number 1, not an alcohol. So these 2 are ketose-aldose isomers, right? They're the same carbon, hydrogen, oxygen combination. They just have them in different locations, so they're isomers of each other. So we can convert DHAP into GAP by going through this enediol intermediate, where we protonate the oxygen and carbon number 2, and we form a double bond between carbon 1 and 2, which would be the enol. Forgot the E. E-N-E, diol. And as the name implies, right, it's an isomerase, which means it converts between 2 isomers. So the interesting thing about triose phosphate isomerase is that it is a catalytically perfect enzyme. Reaction rate is limited only by diffusion. All right, so when we talked about enzymes, it seems like forever ago. The best enzyme out there is rate limited only by diffusion. And this is the example of that. Question?
What is it? Next to the intermediate.
The same word here, ENE, diol. So this rate of the reaction is limited only by diffusion, how fast that DHAP can actually enter the active site by floating along, how fast it takes to float and convert over. Let's see what else is interesting about this enzyme. The delta G of this reaction is approximately 0. Is it perfect equilibrium?
So you can go back and forth.
It could go back and forth. So what would prevent this enzyme from just converting gap to DHAP, DHAP to gap, just flipping back and forth?
So intermediate.
The intermediate. And then what would keep the intermediate from just like hanging out in the active site? What would force this reaction to keep going? Excellent question. I'll write down the answer up here. Okay. So if it's exactly at delta G is 0, it's catalytically perfect. It could just move gap to DHAP, DHAP to gap, just flip them back and forth over and over and over again. Concentration. As gap gets used up later in the cycle, it's going to want more gap from the top. So it's going to funnel more of the DHAP through to make that, to eventually make pyruvate. So as we use gap in other reactions, so farther down glycolysis, we're going to have to convert more of that DHAP to gap to keep using it. So it is a concentration effect. So this is the final reaction of stage 1. At the end of our first 5 reactions, so if we're keeping a score, right, the first half is over of this reaction. At this point, we've used 1 molecule of glucose and 2 ATPs. And our final product so far is 2 gaps. So in the second half, we're going to be looking to get our energy back and make pyruvate. Do we need like a halftime break? Ready for the second half? Well, intermission. I didn't call out the dancers or the cheerleaders or anything. No? That's my sports analogy for today. That's it, one. No, maybe we do the entertainment. Entertainment? No. Okay. Okay, fair enough. All right, so the first part of phase 2 is we're going to use glyceraldehyde 3-phosphate dehydrogenase, otherwise known as GAP-DH. It's not a snazzy name, it's like GAP. But it does tell you that's going to work on GAP, right? It's GAP-DH. So it's going to take our GAP and dehydrogenate it as you're thinking about ways to remember this cycle.
That would drive down.
Yes, yes. So we are going to take GAP, which is right here, and some NAD+, and an inorganic phosphate. We are going to dehydrogenate, which means remove a hydrogen. Excellent. We're going to remove a hydrogen and replace it with a phosphate group. So that should make sense. What's going on over here with my NAD? NAD plus is going to NADH plus a proton. And as you remember, hopefully, all right, that's the reaction of NAD plus. NAD plus takes 2 electrons and 1 proton to become NADH. Okay. All right, so this is an exergonic reaction that synthesizes a high energy molecule, high energy 1,3-BPG. So because we have NAD+, it has to be an oxidation reaction. And then it's phosphorylation, you know, because it has phosphate in there. That's a typo. That shouldn't be exergonic. I was thinking that's not right. That should be endergonic. Can't make a high energy intermediate and release energy. That's ridiculous. Preposterous. I'm surprised no one else was like raising their hands. No? Okay. So to synthesize this high energy intermediate, we need an input of energy, which is what the endergonic means. This reaction is about +7 kilojoules per mole. So a fact that should hopefully never happen in your glycolysis cycle is that GAPDH is inhibited by arsenate, which is the inorganic form of arsenic. Right? So you actually, if you were going to inject or ingest arsenic, it would be in this form, arsenate. Arsenate turns off this enzyme irreversibly, just kills it. And it's officially competing with the PI, the inorganic phosphate. Competes with that irreversibly. So one of the mechanisms by which you would die of arsenic poisoning would be your glycolysis cycle would be turned off, which means you're not making any more energy, you're storing up some weird byproducts. So, yeah, Sarah.
For the arsenate, is that a -3 or 2?
3, it's a 3. ASO4, 3 minus. Okay. So now we've made our high energy intermediate. What we're going to look to do is make some more high energy intermediates and then cleave off those phosphate groups to release energy. All right, so here's our 1,3-bisphosphoglycerate, right? We have 2 phosphate groups attached to that. This is our first step where we can cleave off one of those phosphate groups to get some energy return on our investment. Hold on. What do I want to say first? So this step is our first step in the second half that's going to produce some ATP for us. So 1,3-BPG has one of its phosphate groups cleaved, the one off of carbon 1, and it's going to release a large amount of free energy. So you see it's exergonic, and that releases about 20 kilojoules. So, like you did in your homework for today, we are coupling this phosphoglycerate kinase reaction with this reaction, right? They're one right after another. So we make this high energy intermediate and then we cleave off the energy. So this one had a delta G of about +7. This one has a delta G of -20. So if we added those, or how would I sum those together, right? You would add them together. So +7 plus -20. So at the end of these two steps, are you still exergonic or now are you endergonic? You are still exergonic, right? This reaction has enough negative free energy to pull the previous reaction forward. So forces that high energy intermediate to be made. Because otherwise you wouldn't want to make a high energy intermediate. It's a lot of work. But because this one's so exergonic, the previous step, this making of the 1,3-BPG is possible. So, I'll write that down. Yes. What 3-BPG, its consumption, is releasing enough free energy so that its production in the previous step is forced to happen. But the last thing about this enzyme is that we have to have magnesium again, right? Just like we had in hexokinase, We have to have magnesium in the active site to prevent the ADP from being broken down to AMP. So it's going to force the reaction to make an ATP. So phosphoglycerate kinase uses magnesium to prevent the ADP from being hydrolyzed to AMP. Forces it to make it ATP. Okay. Questions? No? All right, and let's talk about what happens now to my 3-phosphoglycerates. 3-phosphoglycerates now interacts with the phosphoglycerate, which makes sense, right? We just made 3-phosphoglycerate. So now it's going to interact with phosphoglycerate mutase. Any guesses on what mutases do? Mutates. Excellent. So it's going to convert 3-phosphoglycerate to 2-phosphoglycerates. There are very few mechanisms that I'm showing. This one I am, because it's really easy. All right, so how this works is that we're going to transfer the phosphoryl group from one position to another. In order to do that, we have to have a phosphorylated histidine in the active site. All right, so here is 3-BPG. And there's my enzyme. So I had 3-PG. Now I have 2,3-BPG. Where have we run into 2,3-BPG before? Hemoglobin. Yes, this is how the inhibitor for hemoglobin gets made. So at this point, 2,3-BPG can float away. There's nothing holding it in there. But we can finish the reaction. and reform our enzyme. Any guesses on what the delta G for this reaction would be? 0. It's freely reversible. So again, what would force 2PG to be the product rather than either one of these two? Concentration. As your body runs out of the 2PG, it'll force this reaction to go all the way to this final step because it needs it. You good on that? Okay. Super complicated mechanism, right? Had one phosphate group, then it has 2 phosphate groups, then it has 1 phosphate group.
You said it's the concentration.
Is a concentration of, like, as your body runs out of 2PG, it'll have to make more. So it'll force it, a little shot lyase this way. Yeah, Victoria.
Is the fact that like PG is related to hemoglobin, like, does that have any effect on glycolysis, or is it just like a little side?
It does have an effect on glycolysis, but it's kind of indirectly. It's not directly related. So I guess somewhere in between. It has an effect on whether or not your body can uptake more oxygen, which, right, in babies, this was better to have 2 3 BPG than it was in humans. And it also depends on, like, altitude. So it's a bigger answer than just yes or no. Yeah. I don't have a real good straightforward answer. So, how about we take a break and have a quiz? Yay! We'll